Good morning and welcome everyone. This is heat transfer lecture number 3, and in this lecture we will be dealing with what? We will be dealing with radiation. In the previous lectures, what we had done was we have covered conduction. Conduction is the mode of heat transfer which takes place basically in solids. Now we move on to radiation. You might think, sir, what about convection? Well, convection is basically you just have to go through uh, a basic definition of convection, and that is good enough for your course. Convection hardly has any problem, so that is why we are not doing convection. We already know what is convection, the mode of heat transfer which takes place in gases and liquids. There is a physical movement of the particle mediums. Hotter gas, hotter water will go up. Colder gas, cooler water will come down. So there is an actual movement of particles. Do we know this? Yes or no?
Yes, sir.
So that is all that you need to know about convection. Conduction happens in solids. Convection happens in liquids and gases. That will bring us to the third mode of heat transfer, which is known as radiation. Now, whenever we use the term radiation, sorry, whenever we use the term radiation, you must remember this term radiation has a lot of meaning. When I use the term radiation, I may mean a lot of things. Now, what are these lot of things that I may mean by the term radiation? Now, radiation is the process by which any body, whether it is solid, and right now I have a solid body, liquid or gas, can emit radiations, can emit energy in the form of radiations. Now, radiation also refers to the process by which this energy is transferred. And remember, to transfer this energy, we do not need any medium. Radiation also refers to the energy itself. For example, if I am saying that this is a pen, at any given temperature, this pen is emitting some energy. That energy which this pen is emitting is known as radiation. The process by which that energy is emitted is also known as radiation, and the process by which this energy is transferred is also known as radiation. So when I say the term radiation, I mean everything. I mean the energy, I mean the process by which that energy is emitted. I also mean the process by which this energy is transmitted. Do we understand this?
Yes, sir.
Term radiations means a lot of things. When I say conduction, conduction is basically the process by which energy, heat energy is transferred from one point to other in a solid body. But when I say radiation, I will mean a lot of things. So that is what is the first thing that you will note down in your what? In your notebooks, the meaning of the term radiation. What do you mean by the term radiation? Or some people may call it thermal radiation. You call it thermal or not, it does not matter, because whenever you use the term radiation, you are referring to everything which comes under radiation. And what is the definition of radiation? The process of the transfer of heat. from one place to another without heating the intervening medium is known as radiation. So when this energy is transferred from one place to another without heating the medium, in fact, it does not even require the medium. This process is known as thermal radiation. Remember, thermal radiation also refers to this heat which is getting transferred. It also refers to the process by which this energy is transferred. It also refers to the process by which this energy is emitted. Do we understand this?
Yes, sir.
Please note it down. I'll give you a minute to note this down. What is radiation? Have you noted it down, bacha?
Yes, sir.
Okay. Then I come to the next slide. Special points about radiation. So everything that we are going to study here are potential questions. They have come before in the exam. They can definitely come once again. The first thing is definition of radiation. As I told you, radiation is the process by which this energy is transferred, but also whatever energy is emitted is also known as radiation. Do we understand this?
Yes, sir.
Medium is not required for the propagation meaning for the transfer of thermal radiation, and they can travel, the spelling is wrong, travel in vacuum. Radiation which passes through any medium, they are slightly absorbed by the medium. So if there is a medium, they will slightly absorb it. If there is vacuum, they will not absorb it. They will not absorb it. Heat radiation are in the infrared range, so it is more than visible. The wavelength is more than visible. Therefore, they may also be known as infrared. So whenever you hear the term infrared, it refers to thermal radiation. The wavelength is greater than that of light. Infrared, more than red. Ultraviolet, less than violet. This radiation travel in the speed light. You can also call it as electromagnetic waves. Have you heard the term electromagnetic waves? Electromagnetic waves are nothing but thermal radiations. Do we understand this?
Yes, sir.
Then these are to obtain a spectrum, we can use this prism. Again, this is just for your knowledge. Radiation intensity is measured by a device known as the bolometer. You remember this name, bolometer. Whenever these radiations fall, they will exert the pressure. This pressure is known as radiation pressure. You will have to, since it is too much, I will just give you time to note down the important points. Every point is a potential question. Please note them down. There's nothing that you can understand here. It is all about you remembering a lot of these points. I'll give you a minute to note them down. Remember one thing, when I told you that these are electromagnetic waves, light is also electromagnetic wave. You can also call light as thermal radiation. It also has energy. It can also heat up. These thermal radiations or electromagnetic waves, they travel with the speed of light because light is also an electromagnetic wave. Will you remember this? This radiation or any type of radiation, any type of electromagnetic wave follows inverse square law. That means the intensity is inversely proportional to the distance square. The farther you go from the source, the intensity or the energy emitted or energy received per unit area, per unit time becomes less and less. If I go to a distance twice, intensity will become 1 by 4. If I go to a distance 3 times, the intensity will become 1 by 9. Please note this down. Note down that thermal radiations are electromagnetic waves. They travel in with the speed of light. They travel in a straight line. This is the fastest mode of heat transfer. It does not require any medium, and all types of body will emit thermal radiations. I'll give you a minute to note everything down. If there is any problem, anything, please let me know. All these are potential questions that are going to come in your exam. Have you noted it down, beta?
A minute, sir.
Okay. I'll give you 1 more minute to do it. While you are noting it down, I don't know whether you are writing the entire thing. I guess you are all noting it down in your sheet. Please read what you are noting. Please give it time to read. Once you read it slowly and steadily, once or twice, these things will get into your head. Just marking it without reading it will not make any sense. If you don't have the time to write, at least read it once or twice or 3 times. Do we understand this? Whatever time we are spending in the class, that has to be utilized to the maximum. This is the way you can utilize it. If you don't have the time to write, read it 3 times. Read it 3 times, and I'm sure that something will be there in your head. You will be able to recollect it. That is why I'm giving you time. Okay, let's move ahead. Again, some information right now. What are the devices which are used to measure thermal radiation? The name that you have to remember is the bolometer. This is the name that you must remember. The other names are also there if you can remember them. Well done. Differential air thermometer, thermopile, Crookes radiometer, and Boyle's radio micrometer. These are the devices to measure thermal radiation. I have also told you pyrometer or pyrometry is the branch of physics that deals with high temperature. Pyrometer is a device that is used to measure high temperature. Again, note this down. What you got to remember from my understanding is the name bolometer and the name pyrometer. At least you must remember at least these two names. If you can remember them all, it's very good. I'll give you a minute to digest it. Let's move ahead. And let us move to the two types of radiation. Again, a numerical can come on this. I have seen numericals on this, and that is the reason I am taking this topic. This is known as a type of thermal radiation. This is not a type of thermal radiation. It depends on how this thermal radiation is falling on a body. Plain radiation, oops, the radiation that falls at 90 degrees. You can see it is falling perpendicular to the surface. Do we see this? It is perpendicular to the surface. That type of radiation is known as plane radiation. If it is not perpendicular, it is known as diffuse radiation. Do we understand this?
Yes, sir.
Now, whenever radiation is an energy. Radiation consists of, you can say, photons. Whenever they are falling on the surface, they will exert a pressure. Yes or no? You've already noted it down that radiation exerts pressure. Now, if it is a perfectly reflecting surface, whatever is falling in, same thing will be reflected. The pressure exerted will be 2 times U. If it is perfectly absorbing, the pressure will be U. Now you were asking me what is U? U is the energy density, energy per unit volume, energy divided by volume. If it is diffuse radiation, for perfectly reflecting, it is 2 times U by 3. If it is perfectly absorbing, it is U by 3. Draw the two diagrams. Don't mark it in the sheet. This is not for marking on the sheet. Draw the diagram, write plane radiation, diffuse radiation, and write the formula for pressure on the surface P. I will give you 2 minutes to do this. How this formula is derived is none of our business. We just have to remember the formula. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note it down. Have you noted it down? Can you move forward?
Yes, sir.
Okay, now comes this table, and you should not forget this table ever. This is the increasing order of wavelength. This is the increasing order of wavelength. Do you see this increasing order of wavelength? Depending on the wavelength, how these radiations are ranked, the wavelength with the lowest wavelength, the smallest wavelength is cosmic rays, then we have gamma rays, then we have X-rays, then we have ultraviolet, then visible which or violet is the lowest, red is the highest, infrared, which is thermal radiation, our topic of interest, then we have microwave, and at the top, at last, with the largest wavelength, we have radio and TV waves. Here are the wavelengths written 1 Armstrong unit, 100 Armstrong unit. The visible range is around 4,000 Armstrong unit. The width is 4,000 Armstrong unit. Then from 7,800 Armstrong unit, we start the thermal radiation. It goes to 4 into 10 to the power 6 Armstrong unit. And after that, it is all radio and TV waves. Do we understand this? You may not remember this, but you will have to remember this sequence. Cosmic, gamma, CG, X, U, V, I, M, R, whatever is your way to remember it. Please remember this. This is what is required, because I have seen questions coming on this, which is shorter, which is longer, and that is why you need to remember this. Draw this table, may not be the wavelength, they might not ask you the wavelength, but they can always ask you which is lower and which is higher.
Done, sir.
Okay, now remember, in this chapter that we are discussing, everything depends. In all the chapter that we have discussed so far, everything depends on your understanding or the knowledge or whatever you know, what you don't know. In this particular chapter, everything depends on the definitions. There are a lot of terms, probably new terms, probably something that you have already read. A lot of terms will come. If you understand the meaning of those terms, then only you will be having a hold of this chapter. You will be able to solve questions or answer any question. Most of them would be theory based. They are based on the definition of the terms that you get to see. If you understand the definitions correctly, this chapter would be very easy. If you get confused in the definition, which someone might at some point in time, that is why you need to repeat, keep on going back to these definitions every now and then. So please write these definitions. Do not mark them. Write the definition correctly in your sheet as you understand it. It is not important that you write it in English. It is important that you write it in your own language, but it has to be clear. Do we understand this?
Yes, sir.
The first definition that we are going to understand is whenever thermal radiations fall on a body. When I say thermal radiation, it is energy. Now, whatever definitions we are studying here, they are true for any energy which is falling on any body. Light energy, sound energy, heat energy, whatever energy. We are right now we are calling it radiation. We may call it something else. Now, we have one term which is energy density, which we have already used. Energy density. Whenever it is density, it is something divided by volume or something divided by area or something divided by length. Do we understand this? So whatever is energy, if I have a body and let us take the example of a body. Where is the body? Here I have a body. This is a sheet. This is a book. Here I have a body. Now as you can see radiations are falling on this body. Yes or no?
Yes, sir.
If I take a unit volume of this body, whatever energy is falling on this body is known as energy density, energy per unit volume. Now, when energy falls on this body, it does not fall of a single wavelength. As I told you, energy has a lot of wavelengths. We have just seen the wavelength starting from cosmic rays to radio waves. The wavelength of this energy which is falling can be anything. Yes or no? Starting from very low value to very high values. Yes or no?
Yes, sir.
So whatever, it may be of different wavelengths. The energy is falling of different wavelengths. Whatever total energy is falling per unit volume is known as energy density. Now, here what will happen is in almost all the definition you will come across a term spectral added to that term. Here spectral energy density. Now, whenever this term spectral comes, and please remember this, bacha, whenever this term spectral comes, it means that how much energy or how much whatever, here it is how much energy density of a particular wavelength is falling. As I told you, radiation is falling on this body. It can be of different wavelengths. For one particular wavelength, how much energy is falling will be known as spectral. Do we understand this?
Yes, sir.
That is known as spectral, and it is divided by U lambda. Total energy density is U. Spectral energy density is U lambda. Lambda written. This lambda tells us that this is for one particular wavelength. Do we understand this?
Yes, sir.
And the relation between U and U lambda is in this form. This is always the relation between any full term and any spectral term. Spectral term integral will be equal to the full term. Do you see this formula or should I enhance it? Do you see this formula in the
Yes,
sheet?
sir. Yes, sir. Yes, sir.
Okay. And remember, wherever this formula will come, and this thing will come at least thrice, wherever this formula will come, you can draw a graph. You can draw a graph between lambda and U lambda. And this graph would be something like this. If I find the area under this graph, my dear friends, if I find the area under this graph of U lambda and lambda, I will show this graph twice more. Graph between U lambda and lambda. The area under this graph will give me the total energy density, because wherever we have integral is nothing but area under the graph. Do we understand this?
Yes, sir.
I'll give you a minute to note this down. These are very, very important things. A question will come on this, and I can tell you not many students would be able to answer it. A minute to note it down. Have you noted it down, bacha?
Yes, sir.
Okay. Now let us come to the next part of this. And the next part of this relies on reflection, absorption, and transmission. So what are we going to see here? Do you see this Q amount of radiation is falling on this body? Yes or no?
Yes, sir.
When radiation falls on any body like this, only three things can happen. What are those three things that can happen? It can get reflected, it can get absorbed, or it can get transmitted. Yes or no?
Yes, sir.
QR is the amount which is reflected, energy which is reflected. QA is getting absorbed. QT is getting transmitted, total Q will be equal to QR plus QA plus QT. Yes or no?
Yes, sir.
If I divide it by Q from all sides, QR by Q, QA by Q, and QT by Q is equal to 1. Yes or no?
Yes, sir.
This QR by Q is known as R. This QA by Q is known as small a. This QT by Q is known as small t. What is this small r, small and r and small a and small t? I will let you know in a minute. Just note this down. Can you note this down?
Yes, sir.
R plus a plus t equals 1. I will give you 2 minutes to note it down.
Done, sir.
Do we understand this? Have you written this, bacha?
Yes, sir.
Okay. Now comes the time where we understand what do you mean by this QR by Q, QA by Q, and QT by Q. Again, as I told you, this chapter is all about remembering the definition. And these are 3 definitions that you should remember. Reflective coefficient or reflecting power or reflection power is R, which is equal to total amount of energy reflected divided by total amount of energy falling. Do we understand this?
Yes, sir.
Absorptive coefficient or absorptive power or absorption power is nothing but small a, which is nothing but total amount of energy absorbed divided by total amount of energy falling. Do we understand this?
Yes, sir.
Similarly, transmittive power or transmission power or transmittive coefficient small t is qt, total amount of energy transmitted divided by total amount of energy falling, q. And we know that r plus a plus t is equal to 0. Do we understand this?
Yes.
If T is 0 and A is 0, it becomes a perfect reflector. If T is 0, R is 0, it becomes a perfect absorber. If R is 0, A is 0, it becomes a perfect transmitter. A perfect absorber is also known as an ideal black body. We will understand what is a black body. A perfect transmitter is known as diatherminous body.
Sir,
Yes, Pacha.
R plus A plus T equals to 1.
Oh, sorry. R plus A plus T is equal to 1. Slip of tongue and slip of pen, whatever you call it. I'll give you a minute to note this down. Do not waste your time. Have we noted it down, dear friends?
Yes, sir.
So fast? Well done. Well, as I told you, this chapter is all about definition. We have just now seen the definition of A, which is QA by Q, total amount of energy absorbed divided by total amount of energy falling. Remember, when we talk about total amount of energy, it is energy of all the wavelengths. Do we understand this?
Yes, sir.
But again, we can always make a term which is spectral absorptive power, A lambda, which will refer to monochromatic absorptive. That means for a particular wavelength, how much energy is falling, how much energy is absorbed for a particular wavelength divided by how much energy of that particular wavelength is falling. Do we understand this?
Yes, sir.
Do we understand the relation between A and A lambda? A will be integral from 0 to lambda of A lambda, L lambda. Do we understand this?
Yes, sir.
For an ideal black body, what is a black body? We'll come to that. A and A lambda will be equal to 1. A or all this term R, T, they are ratios, they are unitless. Do we understand this?
Yes, sir.
If I draw a diagram, between what and what? Between A lambda and the graph will look like this. What will be the area under this graph? Give me. What will the area under A lambda and lambda ka graph give me? Area under A lambda and lambda wala graph, what will it give me?
A equals to
This area will give me the total absorptive power. Yes or no?
yes, sir.
Yes, sir or no, sir?
Yes, sir.
1 minute, sir. Write it down, sir. Draw it in the book, sir. Draw the graph in the book, sir. Please don't forget it, sir. Have you noted it down, bacha?
Yes, sir.
Yes, sir. No, sir. Then, sir, one problem, sir. I hope everyone does the problem, sir. Total radiation which are incident on a body is 400 joules. Energy of total radiation. 20% radiations are reflected. 120 joule is absorbed. Find out the percentage of transmittive power. Transmittive power can be written as a ratio. It can also be written as a percentage. I hope you understand the question. It's pretty damn simple. I'll give you a minute to solve it so that I understand that you have understood the concept of absorptive, transmittive, and reflective power. I'll give you a minute to do it. Any answers here? No answers? How much is the transmittive power?
Yeah, bhai.
Yes?
50%, sir.
50%. That is the answer. I hope you have not seen the solution and you have solved it on your own. Total amount of energy is equal to QT plus QR plus QA. Total energy is 400, already given. 20% is reflected. I find the 20% of 400, that will be 80. Do we understand this?
Yes, sir.
120 joules is absorbed, so I write 120 here. From here, I can find out the value of transmittive energy that is transmitted. It is coming as 200, but I don't want this value. I want it in percentage. 200 is transmitted, 400 is falling. Therefore, the transmittive power becomes 200 divided by 400 in ratio. In ratio, it is 0.5. In percentage, it is 50%. Do we understand this?
Yes, sir.
I'll give you a minute to note this down. Have you noted it down?
Yes, sir.
If we have noted it down, then we come to the next heading. Remember the way in which things are given in your sheet and the way. But what do I mean when I say the way? The sequence in which I am taking the class is somewhat different. I'll only take the class in the sequence which I feel is good. Notes were made by me, but the sequence is different. Okay, the next heading that you will write is Prevost theory of exchange. Now, what is this Prevost theory of exchange? Now, this theory of exchange, and this is not done, this theory of exchange is applicable to all bodies at all temperature other than 0 Kelvin, absolute zero. Apart from absolute zero, this law is applicable to all bodies at all temperatures. And what does this law state? According to Prevost's theory of exchange, at every possible temperature, there is a continuous heat energy exchange between a body and its surrounding, and this exchange carry out for infinite time. Or, in short, I can say every body at all temperatures is emitting thermal radiation. So you can write it in this way also. I am a body, I am at a temperature, I am emitting thermal radiations at all temperatures because I am not at 0 Kelvin. This is a body at some temperature, it is emitting thermal radiations. But at the same time, it is also receiving radiations emitted by the nearby bodies. Do we understand this?
Yes, sir.
I am a body, I emit radiation. Everybody emits radiation at all temperatures apart from 0 Kelvin. But at the same time, I am also receiving radiations. These radiations which I am receiving, I can either reflect, see some part is getting reflected. I can either absorb, some part is getting absorbed, and some part might go transmitted from my body. It's not an X-ray, it will not pass through my body. But again, I'm emitting radiations and I'm also receiving radiation. This is known as Prevost theory of exchange. Have you written it down?
Sir.
Noting it down is not good enough. You will have to write it in your sheet because it is a very important theorem, very important statement, very important theory that tells us very complicated things in very simple way. Now you can understand when will a body become hotter or when will a body become colder. For example, if I have a chilled bottle of cold drink and I keep it here, after some time it will become hot. It will come to room temperature. It was colder, it will come to room temperature, it will become hotter. If I have a hot cup of tea, which probably I'll have after this class, but if I keep it in surrounding for some time, it will become colder. It will again come to surrounding temperature. Hot tea becomes colder, but a chilled water of bottle becomes hotter. Do we understand this?
Yes, sir.
Now, how can I explain this using Prevost's theory of exchange? When a cold body is placed in a hot surrounding, a chilled bottle of water is placed here, it will radiate less energy and absorb more energy. Do you understand this? I will emit more, I will emit less and absorb more, and therefore my temperature will increase. Do we understand this?
Yes, sir.
When a hot body is placed in a colder surrounding, I will emit more, radiate more, but absorb less, and therefore my temperature will decrease. Yes or no?
Yes, sir.
If I radiate and absorb at the same rate, I'm radiating 5 joules of energy. I'm also absorbing 5 joules of energy. My temperature will remain constant. Do we understand this? This
Yes,
is
sir.
what you will note down. When does a body become hotter? When does a body become colder? It is explained very easily by Prevost's theory of exchange. If I emit more, absorb less, my temperature will go down. If I emit less and absorb more, my temperature will go up. If I do it at the same rate, the temperature will remain constant. I will give you 2 minutes to note this down. Have you noted it down, bacha?
Yes, sir.
What we have understood. Let me give you a quick recap. This is a body. It is not at 0 Kelvin. So what will happen? It will emit radiation. Do we understand this?
Yes, sir.
The process by which it emits is known as radiation. The process by which it is transmitted is also known as radiation, and the energy itself is also known as radiation. Do we understand this?
Yes, sir.
At the same time, it is also receiving radiations emitted by other bodies. Yes or no?
Yes, sir.
Some part of it will be absorbed, some part of it will be reflected, and some part of it would be transmitted. Yes or no?
Yes, sir.
We have seen absorptive power, we have seen reflective power, we have seen transmitting power. What is the next thing that we should see? We have seen absorptive power, we have seen reflective power, we have seen transmitting power. What is the next thing that is left? What is the only thing that is left? No one knows it? Very sad. My heart has been broken, and it's not by a girl. Girls don't break hearts. It's been broken by the students. Very bad. The thing that is remaining is emissive power. I am also emitting. Emissive power written by a small e. Now the other three powers are ratios. They don't have unit, but emissive power is not a ratio and therefore it has a unit. Emissive power is the amount of heat radiation emitted per unit area in 1 second at a particular temperature. I am this body or me. I am emitting radiations at all possible temperatures. How much energy I am emitting per unit area, per unit time is known as my emissive power written by the small letter E. Do we understand this?
Yes, sir.
But when I'm emitting power of different wavelengths. How much energy per unit area, per unit time of a particular wavelength I'm emitting, that will be known as spectral emissive power, E lambda. Do we understand this?
Yes, sir.
And then we also understand that there will be a relation between emissive power and spectral emissive power. Do we understand this? And if I draw a graph between what and what, tell me. If I draw a graph between what and what? If I draw a graph between what and what?
E lambda and lambda.
If I draw a graph, very done, between E lambda and lambda, it might look like this. The area under this graph will give me
Equals
the total
lambda.
emissive power. Do we understand this?
Sir.
Yes or no? No or yes?
Yes, sir.
Please note it down, sir. I'll give you a minute, sir. You will draw the graph, sir. Do not note it down in the sheet, sir. Write it with your own hand, sir. 1 minute, sir.
Done, sir.
We are done. Now is the time that we understand this thing. IBB, ideal black body, Kali body, black body. What is an ideal black body? The absorptive power of this black body is 1. That means it will absorb all the thermal radiations falling on it. Do we understand this?
Yes, sir.
It will absorb everything that falls onto it. It will absorb everything that falls onto it. So it becomes an ideal absorber. Do we understand this? A
Yes,
black
sir.
body is the most ideal absorber of thermal radiation. Do we understand this?
Yes, sir.
And we will also realize that it is an ideal absorber. It is also an ideal emitter. It is the most ideal emitter of heat radiation, because we must understand and write one statement: a good absorber is a good emitter. I will show it to you. I will write it for you here in the sheet so that you can note it down wherever it is possible. And I hope you can see my screen. Yes or no?
Yes, sir.
We have always studied this. A good absorber is a bad reflector. Yes or no? No, yes. If a body absorbs more, it will reflect less, because A plus R plus T is equal to 1. Yes or no?
1. Yes, sir.
If R is high, A will be less. Very simple. At the same time, you must remember that the good absorber, and or I hope you are writing everything that is coming on the screen, the big screen, is a good emitter. So absorption has got everything to do with emission. If I absorb more, I will emit more. If I absorb less, I will emit less. Do we understand this?
Yes, sir.
IBB, matlab ideal black body, is an ideal absorber, which implies that it becomes a perfect emitter. Do we understand this? It is a perfect absorber. It is a perfect emitter. Do we understand this, bacha?
Yes, sir.
This is what you will note down. I'll give you a minute, then we'll go back to that screen and we will note the points of black body. These are the 3 points that you will first note down. Have you noted that thing down that I written on the sheet? Yes or no? No, yes.
Done, sir.
Okay. Then you will note down the things from here. For an ideal black body, absorptive power is 1, reflective power is 0, transmittive power is 0. This is E lambda. What is E lambda? We will come to know. You just write E lambda. Just forget about this. I will give you later on. The nature of radiations emitted from a black body depends on its temperature. It is also known as, these radiations are also known as black body radiations because they are emitted by a black body. Do we understand this? These radiations are known as black body radiations because they are emitted by a black body. Some people may also call it white radiation or full radiation. No one is going to ask you that. At any temperature, the spectral energy distribution is always continuous. That means it will emit radiations of all possible wavelengths. Do we understand this?
Yes, sir.
Please note this down, the important points that I have highlighted. Have you noted it down, bacha? Black body is a perfect or ideal absorber. It is also an ideal emitter. The absorptive power or spectral absorptive power is 1. Reflectance or reflective power is 0. Transmittance or transmittive power is also 0. Do you understand this?
Yes, sir.
Can we move ahead?
Yes, sir.
Okay, just do one change. We have written emissive power as small e. Do not write it as small e, write it as capital E, and spectral emissive power as capital E lambda, because we will be using small e for another term. So I don't want you to confuse it. So just change small e into capital E. Do we understand this? Capital E. Please change small e into capital E. I forgot that. I'm sorry. Capital E is emissive power. Capital E lambda is spectral emissive power. Have you made that correction, bacha?
Yes, sir.
Yes, sir. Then, sir, I come to the next point, sir, and this point has reminded me that I have misplaced and mistakenly written capital E as small e. This comes emissivity, small e. So there are two e's here. One is the small e, which is emissivity. Some people also call it ER, relative emissivity. And one is capital E. Capital E is emissive power. There is a slight difference between these. There is a slight difference between these. Have you written the heading emissivity? Yes or no?
Yes, sir.
Emissivity or relative emissivity, E small e, is total energy emitted by a normal body, people call it gray body, energy emitted by the body divided by energy emitted by an ideal black body of the same type, same size, at the same temperature. So I have this body. This is a normal body. This is a normal body. It is emitting radiations. Do we understand this?
Yes, sir.
Please raise your hands, everyone, so that I see everyone. As I told you, beta, in this chapter, there are definitions, and if you get confused in the definition, we are all gone. So this is a body. It is emitting radiations. The emissive power is capital E. Do we understand this?
Yes, sir.
Now I create a black body of the same size, same shape, same dimension, and this will also emit radiations. Yes or no?
Yes, sir.
A black body. The ratio of these two radiations, the ratio of the energy of these two radiations is known as relative emissivity. So basically it is telling us how good or how black this body is. If this is a perfectly black body, the value will be equal to 1. If it's not a perfectly black body, the value will lie between 0 to 1 because it is a ratio. Do we understand this?
Yes, sir.
That is what is shown in here. Emissivity or relative emissivity. It is capital E of a normal body divided by capital E of a black body. Do we understand this?
Yes,
Emissive
sir.
power of a normal body divided by emissive power of a black body. Do we understand this?
Yes, sir.
It has got no unit. For ideal black body, it is 1. For another bodies, for other bodies, it will lie between 0 to 1. So emissivity is somewhat like absorptive power. It is also a ratio. It somewhat like relative reflective power. Its unit is not there, but there is a difference. Do we understand the difference?
Yes, sir.
Yes, sir. No, sir. Now, if there is emissivity, then there is also one more term that I can define here. I'll give you a minute to think. What could be that term that I can now define with emissivity? I can define a term which is known as spectral emissivity. Do we understand this?
Yes, sir.
Spectral emissivity, and I will write it as small e lambda. Do we understand this? Now, the small e lambda will be the energy emitted by any body of that lambda divided by energy emitted by a black body for the same lambda. Do we understand this? Yes or no? No or yes?
Yes, sir.
Then there will be a relation between this E and this E. This small e will be equal to what?
Spectral
It will be
emissive
integral
power.
from 0 to infinity of E lambda d lambda. Do we understand this?
Yes, sir.
Everything works on the similar lines. If you understand one thing, everything else becomes very simple. If you get confused in any of these terms, the only way to remove your confusion is to read these terms again and again, again and again, again and again, again and again. I will just give you one more term and then I'll give you time to recollect what we have done. I'll give you 2 minutes to go through this, write this, note this down. Have you noted down, bacha?
Yes, sir.
Okay. Then what we will do is we'll move on to this definition, and I hope that this definition makes sense. The next heading that we are going to write is this one, Kirchhoff's law. You might have studied Kirchhoff's law in the chapter on electric current, but here also comes Kirchhoff's law. And what does this Kirchhoff law say? At a given temperature, remember, at any given temperature for all bodies, the ratio, it's not a ratio, but okay, let us call it a ratio. The ratio of their spectral emissive power, capital E lambda. Do we remember capital E lambda? Energy emitted per unit area, per unit time of a particular wavelength. Do we remember this? Capital E lambda, yes or no?
Yes, sir.
To spectral absorptive power, A lambda, energy absorbed divided by energy falling of a particular wavelength is constant, and this constant is equal to the spectral emissive power E lambda of a black body at the same temperature. So I have this body. I hope it will make sense. I will just stop it for a while so that you can just understand what I'm going to say. Let us say that this is a body. It is emitting thermal radiations, yes or no?
Yes, sir.
It is also absorbing thermal radiation. Thermal radiations of one particular wavelength, how much it is emitting, E lambda, divided by of that particular wavelength, how much is the absorptive power, A lambda. E lambda by A lambda for this body is a constant. And how much is that constant equal to? I create a black body, same size, same shape, same dimension, and I find the emissive power of this black body. The emissive power divided by absorptive power of any body will be equal to the emissive power divided by the absorptive power of a black body. Absorptive power of a black body is 1. Do we remember this?
Yes, sir.
That is known as Kirchhoff's law. I hope I have made sense of what I was telling you. Yes or no? Have I made sense?
Yes, sir.
If I have made sense and I have not talked nonsense, then I'll give you a minute to note it down, because then I will write it in terms of equations, and probably I will make more sense or less sense depending on how you look at it. I'll give you a minute to note it down. You will have to note it down. You cannot mark this. Have you written this down, bacha? No? Okay, I'll give you one more minute.
Done, sir.
Now is the time to move ahead and write it in terms of equation. I hope you can see my screen. So what is this Kirchhoff law telling us? It is telling us that A lambda divided by E lambda divided by A lambda for any body at a given temperature is a constant. Do we understand this?
Yes, sir.
And this constant is nothing but equal to, if I create a black body, it is equal to the ratio of, it's not a ratio, E lambda by A lambda. Do we understand this?
Yes, sir.
But A lambda for a black body is 1, so I can simply write it as E lambda for a black body. So you will have to note this entire thing down. I hope that you will be doing it to the best of your ability. Yes or no? No, yes.
Yes, sir.
I'll give you a minute to note it down. But before giving you this thing, so basically what I have now is this equation, E lambda divided by A lambda for any body is equal to E lambda for a black body. Now this equation can be written in a different form. Instead of using lambda, I can use the total emissive power. So I can also write this equation like this: E by A for any body, the ratio of E by it is not a ratio, is equal to E emissive power of a black body. We can also write it in this fashion. Instead of using spectral term, I can use the total term. Do we understand this?
Yes, sir.
Do we understand this?
Yes, sir.
Okay. So this is the second way in which I can write the same thing. I hope everyone is noting it down. Yes or no? No, yes.
Question repeat, sir.
You're noting it down? Yes or no?
Yes, sir.
Yes, sir. So I'll just make it in a box. And this is the box. Okay. Now let us look at this. I hope you have noted this down.
Sir.
Yes, sir. No, sir. Better I go, sir.
Then, sir.
I can't hear you, sir. Okay. If I go back to the definition of spectral, if I go to the ratio, if I go to the definition of emissivity of a body, emissivity of a body was the ratio of emissive power of the body divided by the emissive power of black body. Do we remember this? That was the definition of emissivity. Yes or no? No or yes?
Yes, sir.
Now look at this. Look at this. E of the body, E of the black body. I can bring this thing down and I can bring this thing up. If I can do that, I can write here like this: emissive power of the body divided by emissive power of the black body is actually equal to the absorptive power of the body. Yes or no? No or yes? Do
Yes,
we
sir.
understand what I have written here? From where I have written it? I have written here from the Kirchhoff law. Do we understand this?
Yes, sir.
Now, are both the things looking similar? Are they same or not? This implies that, this implies what? This implies that the emissive, not emissive, the emissivity of the body is equal to the absorptive power of the body. Do we understand this?
Yes, sir.
If we understand this, that means it will imply that good absorbers are also good absorbers who have high absorptive power are also good emitters. Do we understand this?
Yes, sir.
And this is the entire point of discussion here. Kirchhoff law is basically telling us that the absorptive powers E, A or A lambda. I have written this equation in terms of E and A. I can also write it in terms of E lambda and A lambda. Do we understand this?
Yes, sir.
No matter how I write it, basically what I mean here is that is what? That good absorbers are good emitters.
Sir.
Can I have some raised hand that we understand this? From everyone in the class. Good absorbers are good emitters. Black body, kali body. For a black body, the value of this thing is 1. For a black body, the value of this thing is 1. Therefore, the emissive power will also be equal to 1. Do we understand this?
Yes, sir.
Do we understand this?
Yes, sir.
For a perfectly reflecting body, the value of A lambda will be 0, and therefore the value of E lambda will also be 0. Do we understand this?
Yes, sir.
I'll give you a minute to note it down.
The screen disappears. Oh, okay, sir.
Have you noted it down, beta?
Yes, sir.
Then I come to my favorite part, sir, and here is my favorite part. Let us see this. An ideal black body is, which of the following you think is an ideal black body? An ideal black body is something that is going to absorb everything. Who is going to absorb everything? Do you understand the question? Yes or no? No or yes?
Doctor.
And I'm waiting for your answers, bacha.
D for doctor.
Yes, beta.
D for doctor.
D for doctor. 1, 2, 3, 4. Yes. That is the answer. A hollow cylinder, hollow container would be behaving as a very good black body, may not be an ideal black body, but a very good black body because it would be absorbing almost everything that is falling onto it. Do we understand this? Yes or no?
Yes, sir.
This one. On a clear sunny day, sunny day, sunny day, an object at temperature T is placed on the top of a mountain. An identical object B is placed at the same temperature at the foot of the mountain. Both objects are exposed to sun rays for 2 hours in an identical manner. The object at the top will register a temperature. What will be the temperature after 2 hours? Higher than the foot, lower than the foot, equal, none of the above.
B, sir.
Why, sir?
B for Bombay.
Why B for Bombay? Why B for Bombay? Why not A for Ahmedabad? Why not C for Calcutta? Why not D for Delhi? Tell me. Why it would be lower than the object at the foot? Why? They are both at the same temperature. They are both exposed to sun rays for 2 hours in an identical manner. Why?
Reflection from ground, sir.
Reflection from ground.
Reflection of heat.
No, I don't understand.
Reflection of heat from ground.
Reflection of heat from ground. No. Why would it be reflection of heat from ground? Whether it's placed on the top or the bottom, why? Why does it? It has got nothing to do with what. You'll have to look at the height. Probably. Now, the object at temperature T is placed on the top of a high mountain, and identical object B is placed at the same temperature at the foot of the mountain. Now, whether it's placed at the top of the mountain or whether it is placed at the foot of the mountain, after some time they will come to the same temperature, which is the temperature of the surrounding. Yes or no? Yes or no?
Okay, sir.
Now, where will the temperature be higher or where will be the temperature lower? The foot of the mountain or the top of the mountain? When you go up the mountain, the temperature decreases over, right? Yes or no? No or yes?
Yes, sir.
In summertime, you go on hilly stations, na beta? You go on hilly stations, na? Why? Because you feel a lot colder.
Yes, sir.
Therefore, the temperature of the object that you have placed on the top of the mountain will be somewhat lower to the temperature of the object which is placed at the foot of the mountain, because the temperature at the foot of the mountain is always higher compared to the temperature at the top of the mountain. Do we understand this?
Yes, sir.
So that is how you have to think. They will both come equal to the temperature of the atmosphere which is around them. At the bottom of the foot, that temperature is going to be more. Top of the mountain, temperature is going to be less, and therefore the object at the highest point will have lower temperature. On that note, I will end the class today. We will meet tomorrow and we will continue our journey into this chapter on radiation. If you have any doubt, you can please come up. Else, the class from my side is over. Take care and have a nice day. Bye bye.